In case you haven't guessed yet, this chapter is all about bonds. Of course, we're talking not about the bonds shown up top, but instead about the bonds that make up ionic and molecular compounds. We'll talk about two types of bonds in this chapter: ionic bonds that transfer electrons to form the ions that we've already talked about, and molecular or covalent bonds that make up molecules. Because this is general chemistry, we'll treat these two types of bonds as completely distinct, but in reality, there's a continuum existing in between ionic bonds and molecular bonds, with many bonds being somewhere in between. Kind of like the Pierce-Brosnan bond is somewhere between the incredibly misogynistic Sean Connery bond and where you'd actually want a human being to be. Ionic bonds are the easy bonds. Since we've already talked about how ions are formed, we are just saying that the ionic bonds are the forces that pull these ions together. These forces exist in all directions in an ionic bond, and the result is semi-infinite lattices, so lattices that seemingly go on forever, of strongly interacting ions in the solid phase. The actual geometry of the solids has nothing to do with directionality of the forces, and much more to do with best packing, a topic you'll pick up again in second semester with Dr. Vanderwood. As a reminder, ionic compounds can be formed between any two ions of opposite charges. The resulting ionic compound is given in the lowest possible ratio of those ions so that the formula is uncharged. In most cases, simply swapping the charges to give the number of atoms in the subscript gives correct formulas. The exception is when the subscripts share a common factor, like if you have a +2 and a -2 charge that could both be divided by 2. Because ions have small integer charges, that factor is usually 2. We should be able to find the formula for any ionic compound as long as we can identify the charges on the ions. So for example, we know that since beryllium is in group 2, the alkaline earth metals, it will always carry a charge of +2 as an ion. Chlorine is a halogen, so it will always have a charge of -1 as an ion. The formula for a beryllium and chlorine ionic compound is then 1 beryllium and 2 chlorines, BeCl2. Try to identify the charges of each ion using the atom positions on the periodic table, and from those charges, try to identify the formulas before you continue on. Aluminum has 3 valence electrons, being in the first group of the p subshell. It therefore has a +3 charge. Iodine is a halogen, and so it has a -1 charge. Aluminum then needs 3 iodines to balance the charge. Magnesium is an alkaline earth metal, and it loses its 2 s electrons to form magnesium +2. Oxygen is a nonmetal, 2 to the left of a noble gas, so it gains 2 electrons to become O-2. If we simply swap the charges, we'd get Mg2O2, but since MgO is the same ratio but simpler, that's the correct formula. Notice that we just had to divide each subscript by the common factor of 2. Indium can actually have multiple charges, but the most obvious, +3, is from losing the s and p electrons, and that's by far the most common. Sulfur is right below oxygen, so it also has a -2 charge. Swapping those charges gives us In2 for indium-2 and S3 for 3 sulfurs. Thallium is right below indium and also has a +3 oxidation state as its most likely charge. Fluorine, being a halogen, is -1, and the formula becomes TlF3 for thallium fluoride. So ionic compounds are the easy ones. Covalent compounds form when a complete shell isn't formed from the transfer of electrons, but instead is gained when electrons are shared between 2 or more atoms. So beryllium, although it's not actually stable as a covalent compound, just for illustration's sake, beryllium would form a covalent bond if electrons from each beryllium contributed to a shared bond between the atoms. In this case of a shared bond, the atomic orbitals combine to form a new set of molecular orbitals based on the overlap between them to help stabilize both atoms. On the diagram shown, the energy of a bond is plotted on the y-axis, while the length of a bond is plotted on the x-axis. The lowest point along this graph is the least energy that a bond can hold, the most stable form. Bonds are constantly stretching. Farther apart means that the overlap between those atomic orbitals is worse, and the electrons aren't as available to each atom. That would mean that it costs more energy, which you can see on the right of the graph. Shrinking would mean that the closer together atoms and their closer together positively charged nuclei would start to repel. And even though the overlap is better, it would still cost a lot of energy, which you can see on the left side of the graph. So while there is a lowest energy bond length, indicated by, again, the low point in this graph, most bonds move their atoms back and forth around that low point of bond length like a spring. Not every bond is equally stable, and many bonds are not equally shared between atoms. Electrons may be sheared less and less evenly on a continuum straight into ionic compounds where electrons are completely transferred. We mentioned last chapter that the tendency of an atom to attract electrons in a bond, the electronegativity, is a periodic trend with a maximum at fluorine in the top right and a minimum at francium in the bottom left. This is really important for bonding because it tells us to what extent a bond will be ionic, covalent, or somewhere in between. For example, hydrogen and chlorine together, hydrochloric acid, form a covalent bond, but they definitely don't share the electrons equally. Chlorine has an electronegativity of 3, while hydrogen only has an electronegativity of 2.1. The relatively large difference of 0.9 in electronegativity means that electrons will spend more of their time near chlorine and less of their time near hydrogen. Since electrons are negatively charged, this means that the chlorine side of the molecule will be slightly negative and the hydrogen side of the molecule will be slightly positive. We often indicate this in one of two ways. On the left, you see an arrow pointed toward the more negative side, with a positive end modified to look like a plus sign. We do that sometimes. On the right, you'll see each sign labeled with a Greek letter lowercase delta, which is often used to indicate a change. Delta plus is a little bit more positive, and delta minus is a little bit more negative. We also do that sometimes. Differences in electronegativity can cover a pretty broad range across a bond, from absolutely no difference to over 3 units of difference in electronegativity. We define cutoffs, which you can see on the right, arbitrarily. We define pure covalent, polar covalent, and ionic bonds with different ranges. But it's not like there's a drastic difference on either side of a difference in electronegativity of 0.4, which is shown to be the dividing point between pure covalent and polar covalent. Polar covalent bonds that are just over 0.4 are still pretty close to pure covalent bonds, and polar bonds that are just under 1.8 are really starting to look pretty ionic. Again, we always see these as a continuum. Those of you who are paying super close attention to this figure from your book may be worried about electronegativity differences of 0.4 or 1.8. Since this figure 4.8 from your text doesn't actually define those points. If the differences in electronegativity fall exactly at 0.4 or 1.8, the bond is called a double secret agent bond and has both no polarity and full ionic behavior simultaneously. I'm just messing here. We'll make those definitions less than or equal to or greater than or equal to, and it'll make everybody feel better. Now you might be looking around and thinking, I don't really have an electronegativity chart that I can surreptitiously glance at during an exam if I need to know whether a bond is covalent, ionic, or somewhere in between. In general, you can make a few assumptions. Nonmetals with nonmetals tend to be some sort of covalent bond, with nitrogen, oxygen, and the halogens being the most common sources of polar covalent bonds. Notice that these are the same elements that form diatomic molecules, minus hydrogen. Of course, that doesn't catch every possible polar covalent bond, but it does get you most of the common ones. Nonmetals with metals tend to be ionic, and metals with other metals tend to function a little bit differently, with conductive electrons broadly shared that hold together positively charged nuclei. They may have some very significantly covalent character, but the difference in metallic bonding properties are significant enough that we will actually usually talk about these as the dominant interaction instead of talking about covalent bonding. Again, these shortcuts don't capture everything. The rules don't catch everything completely accurately either. For example, the chromium-oxygen bonds in chromate are pretty directional, but the difference in electronegativity would label it as ionic. It's a continuum between these categories, not actually distinct categories. Whatever type of compound we have, we need to have a system to name it so that we can talk about it. We've already talked about getting correct formulas for binary ionic compounds. If we have the formula, the name follows a similar form. For the ionic compounds formed from beryllium and chlorine, we give it the name beryllium chloride. The first part is really straightforward. The cation comes first, and it's just given its name as a cation directly. The second part is from the anion. The end of the word is dropped though, so every anion of a single atom ends in "ide." So along the same lines, aluminum Al(I3) is aluminum iodide instead of aluminum iodine. Notice that we typically don't give any indication of how many cations and anions there are. It's assumed that we know or can figure out the charges of the ions from the periodic table and can figure out ratios from there. See if you can name the remaining 3 ionic compounds before you continue. Magnesium oxide, or MgO, is magnesium oxide, the oxygen becoming oxide. Indium in ion2s3, indium would stay the same, but sulfur becomes sulfide, and thallium in TlF3 becomes still thallium, while fluorine becomes fluoride. Naming binary ionic compounds in this manner is great, as long as we only have one major oxidation state. But what if we have something like iron that has multiple oxidation states, +2, +3, or perhaps even more? This isn't a problem just for iron. Most of the atoms are transition metals, lanthanides or actinides, and have multiple possible oxidation states or charges. In these cases, we still use the same basic structure. The metal name continues to come first and is unchanged. The anion name comes second and ends in "ide" instead of whatever other ending it normally would have. The only difference is that we will now indicate the charge of the metal immediately after the metal as a Roman numeral in parentheses. So the example I chose to show is chromium, which changes colors drastically among its charges or oxidation states. You can see in the beakers 5 drastically different colored solutions of chromium salts in different oxidation states. Here's some more practice with generating formulas and names of ionic compounds. In this case, the cations and anions are mixed between simple and polyatomic ions and singly or multivalent metals. In the first example, the polyatomic ion, uranyl, is one that you haven't seen yet, but that doesn't change the fact that you can balance the formula. The second ion is acetate, which you should know. Each of these ions function as a unit. Since the UO2 +2 uranyl ion has a +2 charge, we can use that charge to be the subscript for acetate, a 2 subscript. The acetate is charged -1, so we know that uranyl's subscript will be 1, which we don't need to show. When you write the formula, the UO2 is written first because it's the cation, and then we put CH3CO2 for acetate in parentheses, so when we write the subscript, it can be clearly applied to the whole ion. The name of the cation again is uranyl, and the anion is acetate. We put cation and then anion, and then we're done. See if you can identify formula and name for the following ion pairs before you continue. The names of the ions that are shown in the next row are iron 3 and sulfate. Sometimes you'll see in old documents ferric instead of iron 3 as well. Since sulfate has a -2 charge, we need 2 irons, and since iron has a +3 charge, we need 3 sulfates. Notice that once again the sulfate goes in parentheses. In the next row, the calcium ion doesn't need a charge indicator, since it really only forms calcium +2. We know that because it's an alkaline earth metal. Phosphate is always -3, so we know that we need 3 calciums to bind 2 phosphates. And again, the phosphate goes in parentheses, so the subscript of 2 can apply to the whole thing. It is named calcium phosphate. Calcium phosphate is the main mineral in your bone, which is about half mineral. Chromium 3 nitrate is just chromium with 3 nitrates. Gold 1 azide has a formula of AuN3. Typically, when a polyatomic ion only has a subscript of 1, it is written as is without parentheses, as is the case with azide. Maybe one of you is wondering, how can I tell that N3 is azide here instead of 3 nitrides? You should always be able to tell the difference between azide and 3 nitrides, -3 charged nitrogens, based on the charge. 3 nitrides would give a -9 total charge, which would require gold to remove 9 electrons to become +9. Only iridium has been shown to be capable of a +9 charge, and only in the gas phase, with no salts being prepared at the time of this recording. In this course, you will not see oxidation states greater than +7, where you'll see permanganate and perchlorate being the only examples that we talk about. If we're naming binary molecules, as opposed to binary ionic compounds, there are a few names that you need to memorize, because nobody uses a systematic form for them. Like water. This list is from your text, but I've removed all the things with just carbons and hydrogens, or hydrocarbons. We have a much more robust system of nomenclature for hydrocarbons and their derivatives in organic chemistry, which is the study of hydrocarbons and their derivatives. We'll learn that system all at once in that class. While we could use the rules that we'll talk about next for any of the molecules with common names, nobody does, including scientists, so it's really important to learn and recognize the common names that everyone knows. If our binary molecule isn't a molecule with a specific common name that applies, the first thing that we need to do is figure out which atom is less electronegative. Like in binary ionic compounds, this will be listed first without changing the ending. Remember, electronegativity is a periodic trend that increases to the top right. You can usually tell which is more electronegative between a set of atoms just by the relative position on the periodic table. If the less electronegative atom occurs more than once in the compound, that needs to be indicated with a prefix to say how many times. This list of prefixes on the bottom right needs to be memorized so that you can recognize these prefixes as they come up in nomenclature here and in organic chemistry. The good news is that you probably already know the prefixes 5 through 10. Those prefixes followed by gon are the names of shapes with that many sides, which many of you have learned in either geometry or kindergarten. After the first word, which is the less electronegative atom, the second word is the more electronegative atom's anion name. For example, instead of chlorine, we have chloride. Instead of oxygen, we have oxide. And we have sulfide instead of sulfur. A prefix is always used for the more electronegative atom, even if there is only one. And if oxide is the more electronegative atom, because it starts with an O, oftentimes we'll blend those prefix names with an O or an A that precedes them. So instead of having monoxide, we have monoxide, and instead of having tetraoxide, we have tetroxide. In our first example, the oxygen is more electronegative than nitrogen. So the N2O, nitrogen, is less electronegative. We can tell that because oxygen is further right in the same period of the periodic table. That means that nitrogen would come first in the name and oxygen would come second. Since there are 2 nitrogens and 1 oxygen, the nitrogen gets the prefix di to indicate 2, and the oxygen, which as an anion is oxide, gets the prefix mono. Altogether, the name is dinitrogen monoxide. The next molecule has 2 hydrogens and 1 oxygen. Hydrogen is less electronegative, and so following the same rules, we'd say that it is dihydrogen monoxide. Dihydrogen monoxide has been found in high concentrations in tumor cells, is linked to thousands of deaths from overexposure every year, and is the major component of acid rain. A public advocacy campaign website is linked that details many other alarming dangers of dihydrogen monoxide. But the website isn't actually advocacy against dihydrogen monoxide. It's instead a clever reminder of how important critical thinking and scientific literacy is in our media consumption. Because if we're paying close attention to our non-systematic names, we'd know that dihydrogen monoxide is more appropriately referred to as water. Of course, water is found in tumor cells, just like every other cell. And we know that thousands of people drown every year from overexposure to water. And of course, water is the major component of all rain, not just acid rain. The media in general does a terrible job with scientific reporting, either to increase viewership or out of ignorance. You, just by being enrolled in a college-level chemistry class for majors, may be among the more scientifically literate persons in many of your spheres of influence, and have a responsibility then to your communities to be able to help them to think critically about what is happening in the world. Anyway, the next molecule, CO2, The carbon gets listed first, since it's farther left in the periodic table and therefore less electronegative. It doesn't need a prefix because there's just one carbon. The oxygen becomes dioxide, making CO2 carbon dioxide. You might have noticed that in every one of our formulas, the less electronegative atom is listed first. This tends to be true and is a good assumption in most cases. The first atom listed is usually at the center of a molecule as well, if there is a molecular center, and usually, but not always, this is also the least electronegative atom. In this next example, carbon is to the left of chlorine, but chlorine is farther down in the periodic table. Both relative positionings would suggest lower electronegativity, so it's unclear just from the periodic trends which is less electronegative. Since carbon is listed first, there is a good chance that carbon is less electronegative, so we can work from that assumption, which turns out to be true. The molecule is named carbon tetrachloride. See if you can identify the final three names before we continue. pH3 is phosphine, a common name that's worth memorizing from the top right. S2F10 is disulfur decafluoride, and N2O4 is dinitrogen tetroxide. Binary molecules containing hydrogen and a nonmetal are often acidic and have names that reflect this. The name starts with hydro for hydrogen, and in the same word contains the root of the nonmetal name with the ending changed to ic acid. So HF is called hydrofluoric acid, the root of fluorine being retained, but the ene part being changed to ic acid. This is true of all of the halogens and is also used for H2S, although hydrogen sulfide is the preferred name for this compound. Similarly, many of our polyatomic ions, instead of being named as hydrogen plus the name of the ion, are named as acids, as we discussed in the last chapter. For all ions ending in ate, the name of the neutral molecule with hydrogens has the ate replaced with ic acid. For all ions ending in ite, this is changed to us acid. All but one of these acid names we've mentioned before when we talked about ions. The fifth entry down is per-iotic acid, related to the per-iodate ion. These are analogs of perchloric acid and perchlorate, with iodine replacing chlorine. When you read it without realizing this, you might be tempted to think of it as periodic acid. Don't do that. Per-iotic acid.